Alright, so this is our lecture number 16, if I remember correctly. Things are kind of starting to get blurry. Okay, so in this lecture we're going to continue discussing about discussion about comparing two populations. We will again discuss comparing two populations of numerical data, but this time around we'll concentrate on the case when the data is collected in a special way, such as, for example, matched pairs. So in the previous lecture we discussed that when we're talking about two populations of numerical data, there are two ways how the data can be collected. Number one, it's possible to collect samples from population 1 and population 2 completely independently. That means that we're taking population 1, taking random sample number 1, set it aside, forget about that for now, and look at the population number 2, again take samples completely randomly, and then we kind of bring them together and run the t-test. Well, if both samples of course behave nicely, right? If they demonstrate normal distribution. Today we're going to discuss cases when the samples are collected in a special way. They are each observation observation in each line, observations in each line in sample 1 and sample 2 are matched by some criteria. So we're going to discuss what can that be. So matched pairs experiment is exactly that. It's experimental data. So in other words, it's a pre-cooked samples. Okay. So in the previous lecture we discussed that the way how it's normally done is usually, not always, but usually, we're getting sample number 1 completely randomly, and after that we're picking sample number 2 in a special way, so that each observation in sample 1 has exactly one matching pair, matching by certain criteria or certain rule, observation from the sample number 2. Okay, so and that's why they're called matched pairs. There are two of them, right? Two samples, and each line numbers are matched somehow. So that's why we call it experimental, because we make a decision how we're going to collect the data precisely, and then after that we go ahead and collect the data. Okay, so let's jump straight into the example. So MBA starting salaries. Question: is there a difference between starting salaries offered to MBA grads going into finance area versus marketing careers? So in other words, MBAs sometimes have concentrations, right? MBA with finance versus MBA with marketing concentration. So question is that true that finance graduates with MBA degree are getting higher salaries than MBAs that are graduating with a marketing concentration? Well, what can affect? So let's kind of take a step back and discuss what can play a role in the initial offer, right? People graduate from MBA program. What can play the role into the how much money they're being offered? Well, one thing is it can be the difference, right, between MBA with marketing concentration versus MBA with finance versus MBA with let's say management or data analytics or whatever that might be, right? So the degree itself, in what field are you going to start working? Another factor might be the GPA. So GPA basically tells the future employers how well did you perform in classes, and if your GPA is low, that's a red flag for them, right? So they're not inclined to offer as much money. So therefore, when we're discussing salaries of MBAs, two things can be at play, right? One thing is it's the difference between MBA with finance versus MBA with marketing. So the field, all in all, and the field by itself. The second factor that might be at play is GPA, right? So it's possible that a person with higher GPA will be offered higher salary regardless of what their concentration was, right? And that is basically an additional factor that can play a role. And we don't want that factor to play a role, because we're asking the question, everything else being equal, is that true that finance graduates with MBA degree get higher offers than marketing graduates with MBA degree? Okay, so therefore we have to somehow exclude the GPA differences, possible GPA differences, from the consideration at all. So this is how it's done in this specific example. Okay, we're going to group MBAs into 25 different groups, right? The first group is people graduating with very close but similar, very close or similar or exactly the same GPA, and that would be from 232 to 236. So second group would be that's supposed to be higher than that, right? 236 to next one is 2.4. Next one is from 2.4 to 2.44, etc. And the last group is from at the top of the class, right? Graduating with highest GPA. So the last range is very close to 4.0, from 3.96 to 4.0. So what we're going to do is this. Instead of just getting a random sample of MBAs with finance degree and another random sample of MBAs with marketing degree, that would be truly independent samples, right? One from cohort number 1, finance grads, and another is from cohort number 2, marketing grads, right? Instead of that, we're going to actually collect the data in a special way. Okay, so from each range of the possible GPAs, we're going to get one person graduating with MBA in finance, and another person from the same GPA range which graduates with a marketing concentration. Okay, and we're going to do the same exact thing with the next group and next group and the last group. So the last two observations would be one person MBA finance with high GPA above 3.96, another person MBA from marketing with also GPA above 3.96. Okay, so this way in our sample, well, it's actually going to be two samples, right? In our data set, each line will represent MBAs, two different people, one with finance concentration, another with marketing concentration, but what's going to be common among them is they have exactly the same really close GPA. So therefore our matching criteria or matching rules in that case is going to be GPA, right? So we're going to pick one person from group 1, another person from group 2, and make sure that their GPAs are really close. Okay, so that's what makes the observations in the same record on the same line to kind of click together, right? So to be very similar, that would be the matching criteria. And naturally, number of observations in sample 1 and sample 2 would be the same, right? If I have one observation in sample 1, there should be a matching observation in sample 2 and exactly one. So therefore, unlike the independent samples, now our sample sizes for sample 1 and sample 2 have to be exactly the same. Alright, so now let's turn our attention to RStudio, right? So first things first, we're going to read data, okay, and the data is in the CSV file, so I'm going to call it MBA underscore salaries, okay, and read CSV from the file C data. The file is called MBA underscore salaries .csv. If I remember correctly, that's the right name of the file. Okay, cool. So let's take a look at the structure of the file, right? So structure of MBA salaries data. So now that we have brought the data from the CSV file into the data frame that sits in the active memory of my RStudio. Alright, so what do we have? We have two variables, two columns. They're called finance, that's the first group, and marketing, that's the second group. Okay, and there are 42 observations in each of the groups, right? So 42 lines, and each line again represents matching by the GPA, marketing graduate and finance graduate. So for example, right here, okay, Because I'm looking at my data set right now, right? The very first group, I don't know, it's probably high GPA, 3.96 to 4.0. A person that we picked with that GPA from finance received an offer of $68,357. The matching person from marketing group, also with a GPA from 396 to 40, received the highest offer of $66,132, right? And all the observations are basically listed in the same by the same principle. So this observation number 2 and this observation number 2, what matches them is the fact that their GPAs are close, right? Now, I want to point out that whatever makes these two observations to click together or match, right, for group number 1 is different than it is for the group number 2. And it's different also for the group number 3 because it's different range of GPAs, right? Now, also what I want to point out is note that as I look across these observations, let me kind of enter a couple of lines here, okay? And I can see that, yeah, in general, finance people are getting higher salaries, right? In this group, the finance grad got more money, the second group got more money, in the third group, here also, but it's not always the case. So, for example, right here, in this group, it's pretty high offer, right? And the person from finance, actually, for this GPA level, whatever that is, actually got about $2,000 less offer than the marketing person, right, with the same matching GPA. So it's not always the case that all finance grads receive higher offer than their marketing counterparts with matching very close GPA. Okay, all right. So here is how the test is done. Okay, when we're performing the hypothesis test, let me kind of let you in on a little bit of the secret, right? How the test is performed. The mechanics of the test is, in case of matched pairs, is different from the mechanics of the test for independent samples. How different is that? Each time when we have matched pairs samples, what really is being tested is one column of data, which is calculated kind of quietly behind the scenes. Okay, so for each pair of matching observations, the software calculates the difference between observation number 1 minus observation number 2 on the same line. So in each pair we calculate the difference between the matching numbers, and therefore we're creating kind of a third column, right? Column of all pairwise differences. And what's being tested really is this one column. So essentially, the matched pairs two population test is performed just like a single column one population t-test, right? And I'm going to actually show you in the middle of this lecture exactly what do I mean by that. But important thing to remember is that we have to calculate paired differences between the matching observations. Okay. Now, here is the important distinction about the independent samples t-test and matched pairs t-test. If you remember from our previous lecture, when we performed the t-test for independent samples, we had to test each one of our sample individually for normality, right? We made sure that sample 1 is normal and sample 2 is also normal. Only then we could proceed and perform the independent samples t-test. Because the matched pairs t-test is performed differently, we're testing the column of differences between the sample 1 minus sample 2. What's important for us is our samples may not be individually normally distributed. We don't care really, okay? The only requirement that we have in order for us to perform the t-test for matched pairs is that the matched differences are independently normally distributed. So in other words, before performing the t-test, we have to calculate the difference between column 1 and column 2, and the resulting column with differences, we're going to have to test for the normality. Okay, and again, sample 1 may or may not be normal, and sample 2 may or may not be normal. I don't care really. Okay, for the t-test with matched pairs, what's important is that the matched pairs differences must be normally distributed. Okay, so let's go ahead and actually calculate that. Right, and I'm going to show you one of the advantages of using RStudio or Python for the data analytics, for that matter. And this advantage is how easy it is to manipulate the data columns, more specifically. Okay, so in my data set I have two columns right now. Right, one column is called finance, another column is called marketing. So as I told you, what I need to do is calculate the pairwise differences. Right, so here's how easy it is to do. Okay, I'm going to calculate pairwise differences between pairwise differences between columns, and record that, and record them into column, which I'm going to name myself. I'm going to name the column differences. Not very creative, right? Okay, so here is how it can be done. And this is basically it all comes from data frame. This is what data frame is capable of doing. Okay, that why is it very beneficial to use data frames? It supports the following operation. I mean, technically, like what would I do in Excel? In Excel, I would calculate a difference between observation 1 and observation 2 on the first line, and then I'm going to copy that formula down, right? So that each row will get the same difference. Here I don't have to do that, right? Here I can do the same, this thing. I'm gonna say in my data set, data frame, which is called MBA Salaries, right? I'm going to say $, and it offers me two columns, but I'm going to create a third column. I'm going to name this column again, as I said, differences, right? So in the MBA Salaries column called differences, right now it doesn't exist, right? I'm actually creating this column right now, and what I'm saying is, in this column, go ahead and record values equal to MBA Salaries column finance minus MBA Salaries column $ marketing. Okay, so what it will do is, for each line it will take one number from salaries, from finance, another number from marketing, subtract them, and record on the same line as the third column. Okay, all I have to do is run this line, and it's done. So now if I want to look at my structure again, let me go up and actually run this line again. Look what happened. So first line, finance, was 68,357, marketing was 66,132, and the difference apparently is 2,225. So if you add that number to that number, you'll get exactly this, right? So it actually did calculate the difference and recorded them in a separate third column. And if you want to see visually, in Excel, for example, right, that it did actually happen, here is one thing that you can do. Okay, if it's easier for you to actually see the data set with your own eyes, sort of, right, you can actually take this data frame and dump it into your own CSV file. So it's done actually. So when we read the file and bring that into the memory, we use the function read CSV, right? Now what I want to do is take the data frame from the memory and create CSV file from that. Okay, so it's a reverse operation, and it's done by the function, guess what? Not read, but write. So I'm gonna say write .csv. Okay, but that will actually create the CSV file for me, right? So I'm making my own CSV file. I'm going to say write the content of my data frame MBA Salaries, right? That's what I have to put into my dump into my CSV file, and now I have to create to specify the full name of the file, and it should be in exactly the same way how we specify the full name when we're reading the file, right? So if I'm going to say dump it for me into the file, well, here I get to name the file, right? I'm going to name it MBA salaries underscore with differences. How about that? With underscore differences. Okay, dot .csv. Okay, if I try to run it like that, well, it does actually run, but I have no idea where to look for this file, right? It is in some default location, which is set as the active working folder for RStudio, and right now I just have no clue what it is, right? So in order for me to dump it into the place where I want it, right, I have to specify the full path again. So it's disk C, folder data, and in the folder data, go ahead and create MBA salaries with difference.csv. Again, this file does not exist. I am creating it right now when I run this line, okay? And it will take the content of my data frame MBA salaries and record that into the CSV file. Let me show you, okay? So I run this line. Nothing happened really visually because it all happens on the disk, right? Okay, so there it is. So here is my C drive, here is my folder data, and I do have the file now that is called MBA salaries with differences. So let me go ahead and open that file. There it is. It's actually created a separate column. That's interesting, right? Created a separate column, which I didn't ask for, kind of enumerates all the paired differences, right? Starting from 1 all the way down to 42. So creates the CSV file in a very special way. Okay, so, and these are the differences. That number minus that number, these are MBAs with matching GPAs, right? Their salaries. Difference is that. And I can verify that, right? So I can go ahead and say, okay, let's calculate that. So one minus another, I should get exactly the same result, and I do, right? And if I go ahead and calculate all of them, you can see visually that differences are all calculated correctly. Okay, so that's basically how we can verify that the operation with the data is done correctly. Well, I don't need that file anymore, so I'm going to delete that. MBA salaries with differences. Alright, so let's go back to our RStudio. Okay, so you know what? Let me actually be meticulous about that. Let's take a look at our flow chart. In the previous couple of lectures, we have discussed that in the previous lecture, actually, right? We have discussed that this is our course, essentially, and I know how to use this this flow chart. This flow chart at the end will tell me which test is the right test to use for my specific situation, right? In my case, I'm comparing two populations. Is that correct? Yes. I'm trying to see if MBAs with finance get an average higher offer than MBAs with marketing. Okay, what data type do I have? Well, clearly it's interval, right? These are salaries. Okay, descriptive measures. Do I deal with central location or variability? Central location, because I'm talking about average salaries, right? That is the central location. Next question, experimental design. Are my data collected as independent samples or as matched pairs? Well, we know the answer to that one, right? Observations are matching because on one line we have two different people with very close GPAs, right? Next question is, are the differences, distribution of differences, are the differences distributed normally or non-normally? So again, for the matched pairs, I have to check only the column of differences, right? I may or may not check the individual samples. It doesn't really matter. As long as differences are normally distributed, I'm good to go. So if they are normal, then I have to use the t-test for mu1 minus mu2. If they are not normal, if differences are not distributed as a bell-shaped normal distribution, and I have to use something that's called Wilcoxon signed rank sum test. This is one of the non-parametric tests that we're going to discuss at the end of this semester. So now big fat question is, I calculated the differences. Are they normal or are they non-normal? Let's go back to RStudio, right? Okay, ladies and gents. So what do I do? So here I need to test differences, pairwise differences, right? Pairwise differences for normality, okay? And so far we use two different methods, right? One of them is visual. Just look at the histogram. So HIST, MBA salaries, and I know that I have a new column with differences. That's what I'm going to plot. Okay, so I'm going to run this. Well, it's a little weird, right? Sure, it's unimodal, right? So there's a big fat mode right here. Okay, sure, it's goes to 0 on the right side and on the left side, but it's not exactly our nice looking bell shape that we're accustomed to. So by just looking at this picture, I don't know what to say, quite frankly. So, well, let me ask two gentlemen, Shapiro and Wilk, right? So I'm gonna say, hey, let's test data for normality, right? And again, null hypothesis for Shapiro-Wilk test is always data are normally distributed. Alternative, data are not normally distributed. So I'm gonna say Shapiro test, and the column that I'm testing is MBA salaries, $ differences. All right, so the p-value is right here, 0.726. That is high p-value, right? And we agreed that each time when we test hypothesis for normality, we always use, no matter what, the standard significance level of 5%, 0.05. So I know that my p-value is higher than 0.05. Therefore, I fail to reject the null, right? P-value is high, the null stays. Fail to reject the null, and my null says that these data are statistically normally distributed. So this shape is not that far different from the perfect looking normal distribution shape. Okay, so therefore let me go back to my analysis flowchart. So I'm right here, right? I know that these are meshed pairs. Distribution of differences, are they normal or are they non-normal? Well, the answer is normal. We just saw it. Therefore, I can go ahead and use the t-test. All right, so I know that I need to use the function t.test, but before we do that, of course, we have to formulate our hypothesis, right? So what is that we're testing? Okay, and on this slide I explain how to dump the data, right? CSV. So this slide explains again exactly what we just did. Testing for normality. All right, so research statement, right? Let's go back to our original problem. Okay, is there a difference between MBA finance versus marketing? More specifically, are finance majors offered higher salaries than marketing majors? In other words, I'm asking here, is that true that average offer for the finance grads is higher than the average offer for marketing grads? And that becomes my research statement, right? So therefore, because it's a research statement, we know it becomes an alternative hypothesis. So my hypothesis that I'm trying to test is average salary for finance grads is higher than the average salary for marketing grads. But remember, everything that we do should be expressed in terms of difference, right? So we're not testing mu1 greater than mu2 or less than mu2. We're testing each time the difference between mu1 minus mu2. So instead of mu1, I'm going to use finance. Instead of mu2, I'm going to use marketing. If finance is higher than marketing, then finance minus marketing is greater than 0. It's positive, right? So therefore, there goes my alternative hypothesis. The average salary from finance MBAs minus average for marketing MBAs is greater than 0. I reverse that statement, it becomes my null hypothesis. Null hypothesis is that no, finance people are not getting paid more than marketing. It's the same, or they're paid on average lower salaries. Okay, so how do we perform the test? So now we have to basically go ahead and do the testing, right? So, well, let me show you in RStudio. Okay, so perform a paired, matched pairs, right? Matched pairs, pairs, t-test. I'm going to use the same root and tutin function t-test as I did before, t.test. Right, and the same exact thing as we did in the previous lecture about the independent samples. Important thing to remember, just like in case of independent samples, all right? If I pick finance column as my mu1 minus mu2, that's the first one, right? And my marketing column as the second one, that's precisely the order that I should feed these columns into my t-test function. Whichever comes first should be going first into the t-test function. So here I'm gonna say t-test, it's MBA salaries, $ finance, comma. The second column is MBA salaries, $ marketing, right? And now I have to say what is mu, but again, just like in the previous lecture, mu here is not mu1 or mu2, but the hypothesized value for the difference between mu1 minus mu2, right? Now we're comparing difference mu1 minus mu2 against 0, and that's exactly what I have to put here, okay? So hypothesized difference between column 1 and column 2 is 0. Alternative hypothesis, so nothing really changed, right? Alternative hypothesis, what is it? Is it greater? Let me go back. Yeah, alternative h1 greater than, right? Greater than 0, okay? So I'm gonna have to say quote unquote greater, but here comes the important difference. And this is basically how the meshed pairs t-test is different from the independent samples t-test, okay? In order for the t-test function to treat these two columns as meshed pairs, I have to specify yet another parameter. That would be paired equals true. That makes sense, right? Samples are paired true. By the way, I didn't tell you that in the previous lecture, but because they're independent samples, then we could just go ahead and say paired equals false. That would mean essentially independent samples. And that is the option by default. So therefore, if I don't say anything, if I do it like this, okay, and just call this function, then it will treat the samples 1 and sample 2 as independent samples by default, okay? But if I do this, I have extra quotations here, right? Greater, okay. If I do this, paired equals true, then now I'm running the independent meshed pairs t-test, right? So let's go ahead and do that. There you go. Okay, so the most important outcome for me is right here. Okay, well actually let's take a look at two of them. So this is number 1. That basically is saying that the mean of the difference of all difference is 3.108.47. So the difference, the average difference between salaries for finance and the salaries for marketing MBAs is $3,108. Okay, so all these differences, when we average them, that's our average. Okay, so it looks like on average, that's my interpretation of this number, right? On average, finance MBAs are paid $3,108 more as their initial offer than marketing MBAs. Okay, over $3,000 difference. All right, but here's my p-value, and I'm looking at that and I'm thinking, wow, that doesn't look like number, right? Well, you should have covered that in the middle school actually. So this number is a so-called scientific representation. Okay, scientific representation of a number. So p-value, I'm going to write it right here. Okay, 1.338 e minus 07. Well, it really means this. It means 1.338 times 10 to the power, I'm gonna put a tilde right here, not a tilde but the kind of I don't know, hat, to the power minus 7. So in other words, it's number with 6 zeros, right? And only then after 6 zeros I have 1, so it's 0.12345 1338. That's the p-value. Okay, this is so-called scientific representation. I actually can let me show you something that I wasn't planning on showing in this lecture, but if you feel uncomfortable looking at these numbers, right, what the hell does that mean, kind of thing, you can turn off the scientific notations. This is how to do it in R in our studio. You can say options and say sci-pen, scientific pen, equals, well, here I'm going to say 99. Okay, so when you run this line, that essentially turns off the scientific notation, or at least if I remember correctly, that's what it does. And if I rerun the t-test, look at that, it does turn off the scientific notations, right? So now my p-value is, instead of 1.338 e minus 7, it gives me 0. How many zeros I have? 6, right? 6 zeros, 1338. So precisely here, what we have here, right? So in other words, for all practical intents and purposes, that is 0, right? Really, really small number, astronomically small p-value, okay? And of course, this p-value is going to be less than any reasonable significance level alpha that we can use. It's less than 1%, 5%, 10%, any of them, right? So what do we do with this p-value? Well, if p-value is small, just like it is right here, we're going to reject the null in favor of alternative, right? Low p-value, less than alpha, you reject the null in favor of alternative. And what does that mean? Well, I found evidence to support my alternative that difference between finance and marketing is positive, which means that finance MBAs are paid statistically higher salaries than their marketing counterparts. Okay, so that essentially concludes the test. Now I wanted to show you a couple of things actually, in order to convince you even more that the test is performed the way it is performed. Now here in my RStudio, I used t-test. This is kind of expanded function, right? I said here's my column 1, here's my column 2. The hypothesized difference between column 1 and column 2 averages is 0. Alternative is greater, and these samples are paired, right? But actually what I told you is this. In actuality, the way how test is performed is from column 1 and column 2, we calculate column consisting of differences between the paired matched observations on the same line, and we're really testing just one column, right? So in other words, what I can do is actually test one single column, which I created right here, column with the differences, and I should get the same result, right? Well, let's do that. Let's see if we can get the same result. So now I'm going to test only one column of differences, right? So testing a single column of differences. Alright, a column of paired differences. Okay. So I'm going to use the same t-test function, right? And I'm testing. What am I testing? MBA data. Oh, MBA salaries, right? $sign. I'm testing this only column, right? And because it's the average difference between the finance and marketing, I'm still trying to see if the difference, the average difference, is greater than 0. So I'm comparing it against 0, right? And my alternative is still greater, right? But I don't have to say paired or not paired, because, you know, there is only one column, right? Paired with what? Paired, there's only one column, there's nothing to pair. So, and when I run this test, guess what? Here is what I just ran, right? On just column of differences, same exact p-value, as you can see. So that basically again just confirms the point that I was trying to make, okay, earlier. The way how the test is performed, even though there are two columns in my data set, the test is performed on only one column of differences, and that's the only requirement, that the differences are normally distributed. By the way, just in out of curiosity, okay, let's take a look. It doesn't really matter, okay, but let's take a look at each column individually, right? So HIST, I'm gonna plot MBA salaries finance. Yeah, it looks pretty good by itself, right? Not terribly abnormal. And let's ask Mr. Shapiro what he thinks. All right, MBA salaries finance. Okay, so I'm looking for high p-value, right? For the data to be normal, p-value must be high, and it is high. So distribution of salaries in finance concentration is normal. And let's do the same exact thing for the second column, right? MBA salaries column marketing. Yeah, pretty good. A little ugly, but overall nothing too abnormal. So I expect Mr. Shapiro to be quite positive on the normality. Let's see, MBA salaries marketing sample. Oh, it's even better actually, right? Even higher p-value, almost perfect 1.0. You don't see a lot of p-values like that. So therefore this data, according to Shapiro-Wilk test, is looking pretty darn normal. So so that's the first thing that I wanted to show you. Okay. Second thing, suppose problem like that comes up on the exam or in the real life situation. Okay, and somehow I just missed the fact that observations are matching. Observations on the same line, they belong to different people with matching MBAs. That's what makes them matched pairs, right? So I just read the problem incorrectly, or I wasn't paying too much attention to that. I'm just, okay, these are independent samples, right? After all, we have a bunch of MBAs with finance concentration with their salaries, and the other bunch of MBAs with finance concentration and their salaries. One group has nothing to do with another group, nothing matches them, so independent samples, right? So what I'm about to do is actually stupid, okay? So don't do that on the exam. Well, I mean, you may have to do that on the exam, but only if the samples are independent. Okay, I'm going to analyze the samples as if they are independently collected. So this is wrong, right? Because data really are matched pairs. Okay, but I'm going to run the t-test. So I'm going to put a comment here. Run the t-test incorrectly as if the samples are independent. Okay, so what do I have to do? Well, t-test, right? Because I tested first sample, it's normal, second sample is normal, so I can do the t-test, right? Let's see what happens. Alright, so t-test. And my first is MBA salaries finance. My second is MBA salaries marketing. And the hypothesized difference mu1 minus mu2 is 0. My alternative is greater, if I remember correctly. Yes, greater, right? Greater. And if I leave it blank right now, then it's going to treat them as independent. But how about I'm going to explicitly state that paired equals true. No, false, right? False. Paired false means independent. Okay, so if I run tests right now, look what happens. My p-value right now is 0.1799. 18% my p-value. It's higher than any reasonable value of the significance level that we can use, right? It's more than 0.01, 1%, 0.05, 5%, or 0.1, 10%. So it doesn't even pass the weak test, right? With 10% significance level. So what do? High value, high p-value. I fail to reject the null, right? In the previous case, when I analyzed this data as paired, matched pairs, right? My p-value was very small, and I rejected the null in favor of alternative. Now, I fail to reject the null in favor of alternative, right? And I get exactly opposite answer. So when I fail to reject the null, my null stays, and what does it say? That finance MBAs do not get higher salaries than marketing MBAs, right? Salaries are the same or even lower for finance MBAs. So my point that I'm trying to make here is this. Depending on how you treat the samples as independent samples or matched pairs, the t-test results might be different. It's not going to be like that always. So I have to be honest with you. These samples were pre-cooked, okay? I specifically made these samples such that if you run the test as matched pairs, you'll get one answer, but if you treat them as independent samples, you'll get opposite answer, okay? It's not always going to be like that. It may be that no matter how you do it, it's always going to be low p-value, or both times it's going to be high p-value. But it's possible that your p-values are going to be different. One is low and other is high, and therefore you will reject hypothesis in one case and fail to reject it in another case. So on the exam, read carefully the problem, okay? because if you use the wrong analysis, you will end up with a different p-value, and you will may come to a completely different conclusion. Okay. Now, how to recognize the case when you have matched pairs versus independent samples? Well, I believe in the previous lecture I made pretty explicit point that it's not about the sample size. It's obvious that sample sizes, when you have matched pairs, must be the same, right? You have same number of observations in sample 1 and sample 2, only then they can be matched. Does that mean that if you have same sample size for sample 1 and sample 2, they must be matched pairs? No. Independent samples can be also of the same size. In fact, sample size, do not use sample size as a judgment point. Think beyond the numbers, okay? Read the problem carefully and try to understand how the data are collected. The answer to the question is that independent samples are matched pairs comes from the description of the data collection process, okay? If it says here's sample number 1, and here is completely different, completely random, nothing to do with sample number 1, my sample number 2, then you have independent samples, okay? But if it says it's people with matching, GPAs, like in this example, or it could be the same person, right? For example, I don't know, drug, right? So cholesterol lowering drug, for example, right? Is it effective or is it not effective? That's actually how a lot of companies, a lot of pharmaceutical companies run their study, right? What can we do? We can basically go ahead and measure a bunch of people, before they take the drug, and then give drug to a different group of people, measure after they take the drug, right? And then as a result, we have independent sample, right? But much more sensible for them would be, how does that affect one person specifically, right? Each person. So you take a bunch of people, they take the drug before, they take the measurement of cholesterol before taking the drug, we record the numbers, then we give them the course of the medication, and after, 3-4 weeks, we measure the same group of people again, and in this case, what makes the observations to be matched? The fact that it's the same person before drug and after the drug, right? So observations on the same line is the same person. That's what makes the samples to be matched pairs. So how to spot if it's a matched pairs experiment? Read exactly how the data samples 1 and 2 were collected. If there is something that matches observations from the first group, the observations from the second group, then you're dealing with matched pairs, okay? And each time it can be different thing. So in fact, we're going to take a look at yet another problem in just 1 second, where you will see another example of what can make observations click together and become matched pairs, okay? But before we do that, last thing that I wanted to address about this problem. I believe we saw when we performed the test right here, t-test, that the difference between sample 1 and sample 2, average difference, is $3,108, right? So over $3,000 MBAs of finance are offered on average compared to their counterparts from marketing. So what I want to do now, for example, is I want to say, well, do the samples provide me enough evidence to state that MBAs with finance concentration are getting paid more than MBAs with marketing concentration by the amount over $3,000. Based on that number, it appears to be true, right? The difference exceeds $3,000, okay? But could it be accidental difference? In other words, due to the randomness of the distribution, due to the variability of salaries, so width of the distribution for both salaries, right? MBAs for finance and marketing. Could be. So therefore, really, what I'm testing, if my question is different, not finance are getting paid more than marketing, but we established that. Are they getting paid more than marketing by more than $3,000? So in this case, here is, okay, I don't have it here, really, right? I thought that I recorded that in my slides, but I didn't. So here, in this case, what I'm testing is this, really, okay? difference between finance and marketing, is it greater than 3,000? That becomes my research statement. Or is it less than 3,000? That becomes my null, right? So nothing really changed except the fact that the hypothesized difference in my null and alternative, instead of 0, it's now 3,000, right? So if I want to see that, all I have to do is go back right here, okay? No, that's the wrong part, right? Paired false, that's independent sample. So I go here, okay? So, and I'm gonna say 3,000, right? Is difference between finance and marketing greater than $3,000 on average? And these are paired, matched pairs, right? So when I run this test, what do I see? I see the p-value of 0.4156. It's high p-value, right? When p-value is high, I fail to reject the null in favor of alternative hypothesis, right? So therefore, null stays. And what does the null say? Let's go back to my slides. No, not this one. Let's go back to slides. My null says that the difference between the finance and marketing is not more than it's less than $3,000, right? So even though this difference between sample averages is higher than $3,000, it's $3,108, right? I cannot claim based on these samples that MBAs in finance are getting more than $3,000 higher offers than the MBAs in marketing concentration. Okay, so my point that I'm trying to make here is that do we always compare mu1 minus mu2 with 0? No, it all depends on what the problem is asking you to do, right? It doesn't have to be 0, but I'm going to revert it here to 0 so that it matches the slide. Okay, so this was problem number 1, and I know that I ran over the self-imposed time limit of 50 minutes, but let's go ahead and take a look at problem number 2, and after that we're done with matched pairs. So problem number 2 is actually pretty interesting, okay? Where is it? PAs, waiters. Okay, this one. Do waiters and waitresses earn same tips or different tips? If I would have to answer that question, I would say probably not the same, because women are, well, they're pretty and everything, right? So therefore people tend to leave more money for them as opposed to waiters. So therefore there is a difference, okay? But of course it's a data-driven world these days, right? So to answer this question we have to actually perform the data analysis. So here's what was done. A restaurant consultant did a study. He recorded the percentage of the total bill left as a tip for the randomly selected waiter and one randomly selected waitress for each of the 50 restaurants. Okay, so again, remember what I told you just about 10 minutes ago. How do you distinguish between independent samples versus matched pairs? It's all about how the data are collected. In fact, you can tell if the problem is about independent samples or matched pairs without ever looking at the data. I'm not going to even look at the data, right? So the way how the data are collected is this. He went to 50 restaurants. So if he goes to the restaurant, he says, give me randomly one receipt for a waitress and one receipt for the waiter. Okay, and then he calculates what percentage of tip was left for the guy and the girl, right? So the common, I believe, standard is to tip 15% of the total bill, right? But he calculates like, okay, what percentage was left behind for one person, one guy and one girl, right? And the fact that both waiter and the waitress, they come from the same restaurant, that makes these two observations click together. That's what makes them matched pairs, okay? The reasoning for that is very simple. One restaurant can be pretty traditional, nothing really special, okay? Another can be some upscale restaurant where, the prices are higher, the service is better. Just generally, richer people go to this restaurant and therefore they are inclined to leave more money as a tip, right? Higher percentage. So if we don't consider that fact, different restaurants are just different in terms of how classy sort of the place is, how expensive the place is, that can become a mixing factor into the study, right? And I don't want the how how upscale of the restaurant do I deal with. I don't want that to become a factor. So I'm going to look at the one waiter and one waitress from the same restaurant. So is it classy or not so classy restaurant? Doesn't matter, right? I'm looking at the same place. And now I'm comparing really male versus female, as opposed to male versus female plus maybe, how classy is the restaurant from observation number 1 versus observation number 2, okay? So the fact that they come from the same restaurant, that's what makes these observations to be matched pairs. And I have to use 1% significance level, and what conclusions can be drawn from the file, waiters versus waitresses. Okay, so let's go ahead and do the analysis. So I'm going to put here a bunch of pound signs to separate. Not a problem, right? So here, well, I won't even say read the data. So tips, I'm gonna say tips data, right? That's what it is. Read file, read CSV from the C drive data folder. I believe it's called waitress. No, waiter. Waiters versus underscore versus waitresses. Something like this. .csv. Sure, I misspelled it. No, actually, it's okay. Alrighty, so let's take a look at the structure of the data, just in case, right? We don't have to do that, but I like to do that anyway. So what we have here is 50 observations, 2 variables, one column for the waiter, another column for the waitress. So I decided, even before I looked at this data, right, I decided that I will consider these samples as matched, just because waiter and the waitress, they come from the same place. That's what makes them kind of match together, right? So let's take a look at the distribution, HIST of the waiters, right? So tips data $waiter. All right, it's okay. I'm guessing nothing too terribly abnormal. Let me use Shapiro test. Again, I don't have to do that, right? Because if it's matched pairs, I'm actually calculating the differences, the third column, and I'm testing this column. So that step is not required. All I have to do really is to test the differences. But what I wanted to show you is, well, you will see in just 1 second, okay? So Shapiro, let's take a look at the tips data for the waiters. And the p-value is, oh my god, look at that. Low p-value. It's below 5%. P-value is less than 0.05. What does that mean? Reject the null hypothesis that the data are normally distributed. It seems like it's normal, right? But Shapiro-Wilk test tells no. It doesn't, it's not actually normal, all right? Statistically, this is not a normal distribution. And if that would be independent samples, by the way, this would be the end of story, right? I would have to say sample 1 is not normally distributed. Let me go back to my flow chart, right? If that would be independent samples, I would say compare two populations. Yes, data type interval, right? The bill, percentage of the total bill, the tip, right? I'm comparing means, so central locations. Experimental design, independent samples. Population distribution is normal? No. Sample 1 is not normal. Bam. Immediately we go here, and I have to use Wilcoxon rank sum test. But I'm right here, right? I'm looking at matched pairs, so really what I have to look at is distribution of differences, right? That's the only factor, okay? So what I'm doing really right now is not important, because I shouldn't even be looking at the distribution of sample 1 and sample 2. Why I did that is to illustrate for you that if sample 1 fails the normality test for independent samples, then bam, we're in trouble. We have to use non-parametric test. Just for the kicks again, let's just look at the second sample, right? Tips data. And that would be waitress. It looks okay, but as I saw just now, appearances might be deceiving, right? Okay, so let's use Shapiro test in order to see if waitresses data are normal. Tips data, waitresses, and yes, it seems that this second sample is normal. Shapiro-Wilks test gives me high p-value, so therefore this shape is normally looking for the Shapiro test, but the first one was not. But that's actually, I could just completely skip that part, right? Because the only thing that is important for me really is test the differences between sample number 1 and sample number 2. So therefore, let me go ahead and calculate the differences. So how do I do that? Same exact way as in the previous example, right? So I'm going to say tips data. Let's create a new column and call it, I don't know, diff this time around. I'm going to call it diff. Okay, equals tips for waiters minus the matching tips for waitresses. And I can even look at the structure of my data for tips, right? And I will see, hold on, didn't type all of it. Okay, bam. And I can see that when I run this line, tips data column called diff is waiter minus waiters. Here's my new column diff. Okay, and what am I testing? Right. So now that I have, I need of course to see if the t-test is even an option here, right? No, that's not the one that I want to look at. All right. So here, right? Compare two populations. True. Interval data, I'm looking at the means or centers, right? Experimental design, they're matched pairs. Waiter and waitress come from the same place. Is distribution of differences normal? That's my big fat question. So let's go back and let's look at the histogram. Histogram is just a visual thing, right? Appearances might be deceiving as we saw. So tips data, column called diff. Not too bad, but now we have to ask Shapiro test, right? Shapiro test tips data, column diff, and my p-value is 0.2345. It is higher than 0.05 standard p-value, so therefore I'm going to have to say that the data are statistically normal. Okay, and that's also an amazing result, right? I take one column which is not normal, subtract another column which is normal, and the result is actually normally distributed. You never know. Alright, so now we can proceed, right? So the answer to this question, difference is normal, yes, and therefore I can use matched pairs t-test for mu1 minus mu2. But what exactly am I testing, right? That's another big question. So let's go back to the main question here is, do waiters and waitresses earn same tips or different tips? That is my question, right? Same means tips are equal to each other, different tips are not equal to each other, right? That's my null and alternative, equal versus not equal. Note that this question is not asking me, is that true that girls earn more tips than boys, right? Or other way around. In this case it would be greater than or less than. What I'm saying here is, are the tips the same or are they not the same? It means that my null and alternative is 0. Difference mu1 minus mu2 is 0 versus non-zero. Okay, so therefore here is what I'm testing. Right? Mu waiter minus mu waitress equals to 0, which means tips are the same versus no, they're not the same. Alright, and before we do anything, let's look at the point estimates, right? If there is a fire, there should be a smoke, right? So if tips are really different, then I should see difference in the averages, right, for the samples. That would be the indication. Okay, so let's take a look. Mean for the tips data waiter is, I can see that waiters are on average paid, in my sample at least, 18.84%. How about waitresses? Mean for tips data waitress, 13%. Well, seems like waitresses, girls, are being paid more, right? But I don't know if this difference is big enough for me to claim really that they're not the same, okay? Because after all, there is variability, right? Not all the girls are paid the same, and same applies for the boys, right? Not everybody paid the same. You can see that numbers are all over the place, right? So due to the fact that each distribution has its own width, it could be that these differences are purely accidental. Okay, so now let me go ahead and use the t-test, right? And again, use matched pairs t-test. Okay, so here's what I'm testing. T-test. All right. The first one, let's see, how did I formulate the hypothesis? First one is waiter, second one is waitress. Alright, let's do that. So here I have tips data, waiter, that's the first column. Tips data, waitress, that's the second column. The difference between me1 minus me2 is 0, right? And my alternative is, how do I say not equal? It's two-sided, right? Two-sided. Okay, that means not equal. But here, another important thing to remember, right? I have to say that this is matched pairs, right? So is it paired data? True, it is paired data. Okay, so let's go ahead and run the hypothesis. I don't think this is the right. Did I do everything correctly? Because I was getting different. No, hold on. Oh, here I posted the wrong paired equals false, right? While it is actually paired. Okay, so I need to change my slides. All right, so this is my where is that? This is my p-value right here. Okay, so paired is true. These are matched pairs, right? And my p-value is small, as you can see, right? So what do I do? And I have to use what significance level? I forgot. Is it 1%? Yeah, at 1% significance level, right? But the p-value is really small, right? It's less than 1%, 0.0005, less than 0.001. So what do we do? Well, alternative hypothesis, true difference. Look at that. Our t-test actually even tells us what's the result of our test, right? We pick the alternative hypothesis. True difference, it means, is not equal to 0. Okay, so therefore, what's the outcome of this test? Well, since the p-value is less than alpha, I reject the null in favor of alternative. And what my alternative? Where is that? My alternative was saying that the difference between waiters and waitresses is not 0, which means that the average tip for the waiter is not the same as average tip for the waitress, right? So my samples, they do provide the evidence that even though it doesn't seem like a big deal, difference is only 1.16% between waiters and the waitresses, right? This is a statistically significant difference. So this sample does provide the evidence that waiters and waitresses are not paid the same. Okay, now let's do what I actually did. So I'm going to replace this slide. Let's do what I did in the slides, right? Let's try to treat these two samples as independent. So therefore, paired, I'm going to say false. Okay, so what happens if we treat these samples as independent? If I rerun the test, here is my p-value, 0.0167. And now my p-value is actually greater than significance, right? Remember, for this test, I'm instructed to use 1%, 0.01. So p-value is higher than the significance value. In this case, I failed to reject the null hypothesis. And what is my null? My null says that the statistically, statistically, average tip for the waiter is the same as the average tip for the waiters because difference between them is 0. So once again, if you use the incorrect test, just like I did over here in the slides, okay, it will it may result in a different conclusions. Okay, So here I tested the hypothesis as if they were the samples were independent, and it gave me the conclusion that waiters and waitresses are the same. And if I treat the samples as matched pairs, the conclusion changes. Okay, so again, on the exam, please be careful about which test you use and how to recognize which one is correct. Read carefully how the data are collected and try to understand, if observations on the same line are matching by certain parameter, criteria, rule, whatever that may be, or are they completely random. Okay, so that concludes our lecture on matched pairs, and in the next lecture we're going to discuss differences, comparison of the two populations if the data are categorical, and therefore we're comparing proportions.